All right, we're getting into some more interesting stuff now. We're talking about vectors. Now, if you've seen Despicable Me, you already know what a vector is. A vector is so a vector, it's a mathematical object. We'll say a quantity that has both direction and magnitude. Now, the one thing a vector does not have is a position, but direction and magnitude are the two kind of characteristics of a vector. Usually it's drawn as an arrow. So, for example, we might have, so I'm going to put in like some axes. I'm going to just do it in 2D for the moment, but maybe this could be a vector, and we might label it with the letter V, labeled with either a bold lowercase letter, but usually we don't have that at our I'm on eraser mode. Oh, there we go. Or so either bold lowercase letter or a lowercase letter with an arrow. For example, like that. If it was on the computer, it would be written, as a bold lowercase v. That's what you'll be seeing in your textbook. So, vectors representing if it's representing the movement from location A to location B, we might indicate it with the at the starting and end point of the points. Like if you have labeled the starting point and end points A and B, we would indicate it with capital AB with an arrow over top. And so here A is the initial point, and B is the terminal point. Got a little messed up there. Okay, so the terminal point and the initial point. So if vectors u and v have the same direction and magnitude, then we say u is equal to v. So vector equality is relying only on direction and magnitude being equal. There's nothing to do with their location in space. Like I said, a vector, the location of a vector, the position of it, is not a characteristic that it has. We can draw a vector. We can draw a vector in any position with any initial point, for example. It's still the same vector. Okay, that's a little weird, but that's the way. I mean, those vectors are equal to each other. So the way we deal with vector addition if we have actually let's do it on a fresh page. If I start at point A, let's see if I can. Okay, so I'm going to start at point A, and we're going to go to point B, and then we're going to go to point C. Now I'm going to put them in nicely with lines, A to B and B to C. So if we start at A and then go to B, we can represent this movement as the vector AB, and then to C along vector BC, the location we're at is the same as if we had started with A and gone to C directly. So this is the way vector addition works. AB plus BC is equal to vector AC, because we care about the terminal, like the starting point and the end point. The net direction and magnitude. All right. So I guess one thing I should point out is the zero vector written like that is the only vector with no magnitude. I'm sorry, no direction. Well, no magnitude either. And its magnitude is zero. It's a vector of zero length, and we don't even draw it with an arrow or anything. It's a concept that is going to be needed on occasion, but it's not something that we really illustrate. Basically, it's a lack of movement is what is the concept that it's meant. It kind of represents. Okay, so let's see a couple more foundational sort of ideas. We have the idea that okay, so if U and V, if U and V, two vectors U and V, are positioned such that the terminal point of U is the initial point of V. Like, this is basically what we're illustrating with the vectors AB and the vectors BC. So this is this would be like the vector U. This is the vector V. This would be the vector U plus V. We're saying that U plus V is the vector with initial point the same as U and terminal point the same as V. Okay. This is called the triangle law, as you could probably see why. Okay, so far we haven't talked about much of real big substance, but we're building on the way that we kind of work with vectors. We haven't really even worked with any numbers yet, just kind of this concept of a vector in space. And only in 2D space so far, but really like the idea in 3D space, well, we're just drawing a line from point to point. So 3D, whether the vector is in 3D or 2D space is sort of not even an issue at this point in time. Okay, so some facts about vector addition. vector addition is commutative. So I should say u plus v is equal to v plus u. And so to illustrate kind of what I'm talking about, so let's have u and v so if this is the vector u and the vector v, if we were to start at this point here and we were going to go in the direction of v, let's see if I can do this. I'm going to paste that here, see if this kind of works. And I'm going to copy the vector u and put that over here. What we get is the same thing. So this from here to here is the vector u plus v, and it's also the vector v plus u. This is the parallelogram law. So starting at some point, going in direction of the vector u for its magnitude, then in direction of vector v for its magnitude, will end you up at the same point as if you did it in the other order. Okay. Then what else? Ooh, okay. So now, so far we've been talking about vectors. Now a scalar is a real number. So every number that we've been dealing with pretty much so far is a scalar. And now we're going to use the term scalar to differentiate those from vectors. Whereas a vector has magnitude and direction, a scalar just has a value, a real number value. That's it. It's a real number, like the number 17. The scalar multiple of vector v, let's for example, let's say c is a scalar. We're going to use the lowercase c. So so if you have the scalar c and then the times the vector v, this is a vector in the whose length is absolute value of c times the magnitude of v, and in the same direction as v if c was greater than 0, and in the opposite direction if c was less than 0. And if c is equal to 0, then CV is just the 0 vector. I'll show you kind of what that would look like. So if this was my vector v, then I'll see if I can put it in red. This would, let's say this would be like 3v, and then I'll do it in blue, roughly that. This would be like negative 1/2 v. If you can see those differences, this, like, they're all kind of illustrated with the same initial point. That's roughly what 3v would be. I mean, I'm trying to illustrate it's about 3 times as long, and it's going in the same direction. Okay. Now, vector difference. To do subtraction of vectors, u minus v is defined as simply u plus negative v. So you go in the direction of u, and then you go in the opposite direction of v. Okay. So if I think it's always useful to kind of illustrate these things, and I'll do my best to do so. So let's have this. Okay, so these two vectors, here's u, here's v. Okay, if I was going to do negative v would be like in that direction, roughly. Negative v, and so this is the vector. So we have over here would be u plus v, and over here is u minus v. That's what those two vectors are going to be, u minus v and u plus v. So in general, we can position a vector anywhere, and so we often okay, we often position the initial point at the origin. So a 2D vector will have the terminal point at the coordinate like a1 comma a2, and a 3D vector will have the terminal point at the coordinates a1, a2, a3. So the idea then is we're going to be using the terminal points of the vector that's been positioned at the origin as the components of the vector. So when we call this actually, let me see. So for any point P in space, the vector OP, origin to that point, is the position vector. Let's fix that a little bit. Of P. So that's what we'll be talking about, position vectors a lot, and it's just a way of really changing our perspective on a geometric object. Instead of thinking of something as a point in space, we'll be looking at the vector that takes us from the origin to the position of that point, and we're going to find that they're going to be essentially the same in every way. It's just a different way of looking at the same geometric object. So we have a way of like talking about components of vector. Now we're going to get into some more nitty-gritty stuff. So given points A at like x1, y1, z1, and point B, which is at a2, not a2, it's x2, y2, z2. The vector v, which is the same as vector AB, has components the components can be written like this. V is going to be the first component, x2 minus x1. It's the difference in the first components of the 2 points. Y2 minus y1, z2 minus z1. Now this is the notation that's commonly used for vectors. We use these brackets. This is always the case. Let's clean that up a little bit. Okay, you'll be using brackets to show vectors rather than parentheses, as would be used for the coordinates of a point. So we have the components of a vector and the coordinates of a point. But as I mentioned, they're really the same thing. It's just 2 different perspectives on the same mathematical object. The magnitude of V, now we're getting into like how we exactly quantify these characteristics of a vector. The magnitude of V is denoted either a single bar or a double bar, depending on the context you're in. They mean the same thing. And the in 2D, the formula is square root of so where V was remember the vector that had components. What did I write? A1, A2, A3. Let's just go back a second to the previous page. Did I put those in? It had the terminal points at A1, A2. The vector would be A1, A2, A3 with brackets. In 2D, if the vector V was just like A1, A2, then the magnitude would be given just by the distance formula, or the Pythagorean theorem, I guess. You could say it's the same thing. A1 squared plus A2 squared, square root of that. In 3D, if your vector V was A1, A2, A3, then your magnitude would be square root of A1 squared plus A2 squared plus A3 squared. All right. So this is how we get the magnitude of the vector. Now, when we add vectors, we add them component-wise. So component-wise addition meaning if I'll give examples in R3. Let's say vector A was the vector A1, A2, A3, and B is the vector B1, B2, B3. Okay? A plus B is going to be, component-wise, A1 plus B1, A2 plus B2, and then A3 plus B3. Sorry for my B's are a little bit sloppy. Okay. Vector subtraction, you'll be subtracting component-wise. A1, you know what I'm going to do? I'm going to be a little bit lazy. I'm going to just select this and copy it. I'm going to just change these things into subtraction signs. All right. And then if you have a scalar times vector A, you're going to be multiplying the scalar against each of the components. CA1, CA2, CA3. Let's see, some properties of vectors. We'll be going to the next page for that. All right, so some of these I've mentioned already. One, the commutative property. I'll just say commutative addition. So vector A plus B is going to be equal to B plus A. All right, because when you're just adding them component-wise, and so you add the components, and components are real numbers, and therefore addition property of real numbers applies to the components, right? Associative addition. So if we have vectors A plus B plus C, if you're going to add vectors B and C first, that's the same as if you were to, the same result as if you were to add vectors A and B first and then add vector C to that. Then we have the additive identity. So the vector, any vector A, if you add the 0 vector to it, you're just going to still have the vector A. The 0 vector is a vector with all components equal to 0. The, let's see, additive inverse. A plus negative A is going to give you the 0 vector. Again, since vectors are built of real numbers, all of these kind of properties are going to follow. In fact, what you will realize is that real numbers are actually just vectors of in one dimension. They're one-dimensional vectors, but we just call them scalars. But all of these things that are true of vectors, kind of when you collapse the dimensions down from two or three dimensions, if you collapse it down to one dimension, the properties still apply. And these are properties that we're already familiar with. Let's see. Distributive scalar multiplication. So if you have some scalar times vector addition A plus B, this is going to be CA plus CB. The scalar would distribute to both of those vectors. Now we have scalar addition. So if you had two scalars, C plus d times vector a. So now we have the scalars that are multiplied, or sorry, added before multiplying. This is the same as if you were to have c times a plus d times a. And we always have to be careful about putting an arrow over top of your vectors to distinguish them from scalars. Let's see, 7, the associative, that scalar multiplication is associative. Ooh, that didn't come out nicely. Okay, so if you have scalars c and d multiplied by each other times vector a, you could just as well multiply d times a first and then multiply by the scalar c. It's not going to make a difference. And then the multiplicative identity. So it's just the number 1 times any vector is going to be that vector. So far, we've been looking at adding 2 vectors, subtracting 2 vectors, multiplying a scalar times a vector. You're probably thinking to yourself, well, what if I wanted to multiply 2 vectors? And that is going to be something we'll cover in the next section. In fact, we'll be covering it in the next 2 sections because there's really 2 ways that we can multiply vectors. We can do what's called a dot product, and we can do what's called a cross product. And there's 2 different ideas about multiplication. Interestingly, both a dot product and a cross product, when you collapse down to 1 dimension, they end up being the same thing, but they're very different things in higher dimensions. So we'll be looking at those shortly. Let's see. The basis vectors. I'm going to draw this as a little picture now. So I'm going to indicate this, hopefully will be a decent drawing. Now in the 3D space, if we go at 1 unit, I'm being a little sloppy, I'm not going to the grid points, but regardless, the vector that goes from the origin out to 1 in these 3 dimensions, this is called the I vector, this is the J vector, and this is the K vector. So I, and this is going to be distinguished from the imaginary number. In this course, we're not actually going to be dealing with any imaginary numbers. So whenever you see I, you can assume it's talking about the I vector. It's the vector with components 1, 0, 0. The J vector is 0, 1, 0. And then the K vector, 0, 0, 1. So we can write vectors using these components. If vector A, A1, A2, A3 can be written as the sum of these 3 vectors, A1, 0, 0 plus 0, A2, 0 plus 0, 0, A3, right? Like you could express it when you add this component-wise. The zeros are gonna just be 0 plus say A1, 0 plus A2 plus 0, and so forth. You can factor out the A1, the A2, and the A3 as scalars. So this second vector, plus A3 times this 0, 0, 1. These vectors are just the I, the J, the K. So A1 times the I vector plus A2 times the J vector plus A3 times the K vector. The point is, any vector can be written as in either component form. This would be like component form, or in terms of the basis vectors. Now, if you were in 2D space, you would just chop off the third dimension, and there would be only two basis vectors. There would be I and there would be J. There would be no K in 2D, and there would be no third dimension, so there would be no third component. But and I'm not going to talk about why it's called basis vectors, but these are the standard basis, I should say. This is the standard basis vectors. There would be other basis vectors that you could use for 3D space, but you'll get into that in a course in linear algebra. I guess the last thing is the concept of a unit vector. A unit vector is a vector with magnitude 1. So as long as your vector is not equal to the 0 vector, you can get a unit vector in the same direction. I'll say unit vector, call it you can get a unit vector in the same direction as A. The unit vector, I'll call it U, is going to be I'm going to divide by the reciprocal of the magnitude. All right, so this is how you would essentially scale the vector so that its magnitude is now 1. And we'll be doing this a bunch of times during the course. We'll have to do something and we'll say, okay, now we have a vector, let's get a unit vector going in the same direction. We'll be doing that a bunch. And so you have to find the magnitude. That's why we spent the time talking about finding magnitude. It's the distance formula. You find the magnitude and you divide it. And what that means is this would be like A1 over the magnitude of A, comma, A2 over the magnitude of A, A3 over the magnitude of A. Oops. Right, so you divide each component by the magnitude of A. Okay, so we'll do practice with this stuff shortly, but in the meantime, that's pretty much it for the basics of vectors and vector addition and unit vectors, like vector scalar multiplication, and so. Yeah, we'll keep going with other stuff in further videos. All right, bye.